Okay. Right. Okay. Good evening. We'll start. Can you confirm whether I'm audible? Audible, right? Right. Okay, right. Fine. Right. All right, then we'll start. So we are in day 13. Day 13 of our S2 discussions, right? And you are 12 weeks from the exam. So we are getting close to the exam day by day, right? Day 13 of S2A and 12 weeks from the exam, right? So last week you were able to finish the matter and radiation questions on photoelectric effect and radiation, right? Blackbody radiation and photoelectric effect. So today I'll be covering, I'm planning to cover particle physics, waves means X-ray questions, and radioactivity, right? Those questions. Today also we have around 37, 38 questions, right? So let's see how it goes, right? Let's see how it goes. So we have quite a few more questions to be covered, right? And my plan is to finish all the questions of matter and radiation by today, because last week we were able to, we managed to finish around half of the questions from all questions, right? Then today my plan is to finish the rest, right? Okay, then without any further ado, let's get into the discussion, right? I'll share my screen. If you haven't get the questions, right, I have pinned a comment here in the live chat. Go there and download it, right? Otherwise, if you are already in my channels, you can download it from my channels, right? And yes, and in the groups also, in WhatsApp groups also, the same link is shared, so you can get it from anywhere, or even in the description of the video, that's there, right? Okay, so let me share my screen. Okay, screen is visible, right? Right. Okay, let's start. First one, which of the following statements made about X-rays is not true? X-rays, right? Now with the questions, you can memorize, you can recall if you are missing any theories about X-rays, right? So X-rays is a part we have covered around 1.5 months back, or around 2 months back, right? Yeah, around 2 months back, right? So if you have any theory parts that you can't recall now, you can recall them along with the questions here. I'll be also like explaining some background about the question also, right? Wherever it's necessary. Okay, first one, which of the following statements made about X-rays is not true? Right, first one, in vacuum, X-rays propagate with the speed of light. Yes, because X-rays is an electromagnetic wave. X-rays is an electromagnetic wave. Any electromagnetic wave propagate with velocity of light, right? Any electromagnetic wave propagate with velocity of light. So it's correct. Second one, X-rays can be diffracted by crystal lattice. X-rays can be diffracted. Yes, it undergoes it does all wave phenomena, right? Reflection, refraction, diffraction, interference, polarization, right? It can do all phenomena. It can do all phenomena, right? So it's also correct. Then X-rays can produce photoelectric effect. Yes, again that is because of X-rays is an electromagnetic wave. X-rays is an electromagnetic wave, right? Photoelectric effect can be done by using any electromagnetic wave. Both on X-rays can be deflected by electromagnetic fields. No. What's the reason? X-rays are neutral. They are neutral. They are chargeless. Right? They are chargeless. Since X-rays are chargeless, they cannot be deflected by fields. Right? Without a charge. Then it's not true. Yeah, it's 4. Then 5 is X-rays can ionize gases. Yes. When X-rays travel through a gas, it ionizes. Right? It ionizes the gas. So answer is 4. Answer is 4. Right? Second one. A proton is fired at an atomic nucleus. Which of the paths shown in the diagram is not possible for the proton? Right. So we know nucleus is nucleus. Nucleus means that is naturally positive, no? Nucleus is naturally positive. Which means now this is the nucleus given here. This is the nucleus given here. It should be positive. Right? A proton is fired. Right? Proton means proton is also positive charge. Protons are also positive. Then positive charges are repelled each other. Then it should repel. Then there cannot be any kind of an attraction towards that. It should be repelled. Right? Now, if you check this given path of S, not C. If you check this given path of S, this one, it is attracted towards the atom. No? This path is attracted. Then it cannot be. It cannot be a possible path because it is attracted. All other paths are repelled somehow. All other paths are repelled. Right? There cannot be any kind of an attraction. So answer is S. There cannot be any kind of an attraction. It's S. Right? A simple logic. 3. When a free particle with kinetic energy K and de Broglie wavelength lambda enters a certain region, its potential energy becomes V. The particle's new de Broglie wavelength is given by. Okay, so we know equation of de Broglie wavelength is lambda equals h over mu. Right? Lambda equals h over mu. Since kinetic energy is given, right? Since kinetic energy is given, we can connect this with kinetic energy easily using one of our famous equations we have in electric fields, right? That is coming from electric fields. The equation is W equals Q delta V. Where W represents kinetic energy. Is Q delta V. Right? Now, to write a substitution here. No need to use delta V because potential difference is not given. Let's go with just kinetic energy equation. Just the kinetic energy is needed. See? Then simply kinetic energy is half mv squared. Say half mu squared. Right? Now in the initial case, kinetic energy is given as K. So let's assume this as K. So if this is K is half mu squared. And I'm going to find the substitution for K. Sorry, U. Then subject U is given by 2K over M square root, no? U is given by 2K over M, it's square root, right? Now, if I plug that here for lambda is H over M U is root 2K over M. Now, this root M to M cancels. See, root M to M cancels. Then final equation I can have here is the modified equation H over root 2mk. H over root 2mk. Where K is kinetic energy. Now I'm going to use this equation for these two scenarios. See, I'm going to use this equation for these two scenarios now. This one. Look at here. I'm going to use this equation for these two scenarios now. Right? In the first scenario, lambda is in the first scenario, lambda is H over root 2mk. No. For the second scenario, say it is lambda dash, that is H over root. Now it says potential energy becomes V. If potential energy is V, kinetic energy should be the remainder. because total energy is simply kinetic energy plus potential energy. Initially, kinetic energy was K, and then potential energy becomes V, then remainder should be kinetic energy. Then this is 2m, remainder means K minus V. Divide these two equations, right? So once these two are divided, H to H cancels, root 2m to root 2m cancels, right? Then lambda over lambda dash, then lambda over lambda dash equals, right? From here, 1 over root K remains. And from the other one, if you put the reciprocal, root K minus V remains, right? We need lambda dash, no? Subject lambda dash. So lambda dash is given by lambda times root K over K minus V, right? That's a tricky question. It's 2. A little bit tricky question. It's 2, right? A de Broglie calculation, de Broglie wavelength. De Broglie wavelength connected with kinetic energy. If kinetic energy is given, since we have velocity here in de Broglie's equation, u, right? So I found a substitution using kinetic energy here and used it as u, right, to serve my purpose, right? That was it. So different types of questions are there, right? Usually questions are connected with potential differences, right? Energies. Now this one is connected to energies, right? There's another type of questions connected with potentials, potential differences, right? So that will be there in the coming ones, right? Let's see. Let's move on. 4. When a beam of 100 kilo electron volts, 100 kilo electron volts, electrons is stopped in a metal target, it produces, right? We know in X-ray production, we have a metal target and electrons are decelerated, right? They are decelerated at the target in the X-ray production. So it is X-rays. It is X-rays directly from X-rays. X-ray production, right? 5. An electron of mass me when accelerated through a potential difference. This is the type I mentioned you. Usually de Broglie questions are given with potential differences also. Right now this is with potential difference. An electron of mass me when accelerated through a potential difference has a de Broglie wavelength lambda. The de Broglie wavelength associated with the proton of mass mp accelerated through the same potential difference would be. Okay. Now, if the potential difference is given, you can first modify the equation like this, right? Using W equals Q delta V if the potential difference is given, right? We know W represents kinetic energy. This is coming from electric fields. Then half mu squared equals Q delta V. Then for U, I can get a substitution here. U is 2Q delta V over M, right? U is 2Q delta V over M, its square root, right? U is known. If U is known, now I can use this substitution in de Broglie equation. That is lambda equals H over mu. Now lambda equals H over M. Instead of U, I have this 2QV or delta V over M. Now this root term cancels. See, root term cancels. This root term to this one cancels. This becomes root term. Then final equation comes here is H over root 2mqv, no? H over root 2mqv. Since we are to apply this equation under two scenarios, I'm going to cut off the constants. Planck's constant is a constant for these two occasions. 2 is a constant. Mass changes, me and mp. Mass of electron and proton changes, right? Mass changes. But Q remains same, no? Because we know electron and proton are having the same charge, but only the polarities are different. So the magnitude is same, Q is cut off, right? Q is cut off. And it says it's same potential difference. This is also off. Then finally, what I have got is lambda is inversely proportional to root m. Lambda is inversely proportional to root m. Then I'm going to use this equation under these two scenarios, right? Then for the first one, if you apply, then lambda is proportional to 1 over, first one is an electron, no? Root me. And for the proton, if you apply, say that is lambda dash proportional to 1 over root mp. Divide these two. That's it. Then lambda over lambda dash is 1 over root me times reciprocal mp over 1. Subject lambda dash. So lambda dash is lambda times root me over mp. Right? Lambda times root me over mp, it's 2. Right? Again, a little bit tricky question. And this is another popular type. Right? This is another popular type when it comes to de Broglie questions. Usually, it is connected with potential differences. Right? So, this is a question with potential differences. Right? Take down if anything. Right? Take down if anything. Okay. Right. Ask if there's any clarifications needed. Right. Ask if you need any clarifications. Right. Let's move on. 7. Which of the following graphs best represents the variation of momentum? P, particle with its de Broglie wavelength. Right. Graphing. It's a simple graph. So we know lambda is HO mu. Mu means momentum. Then this is lambda is HOP. HO momentum. Right. P is subjected. If P is subjected, I mean P is taken to I, then I'm going to subject P. Right. Then P is given by H times 1 over lambda. No? H times 1 over lambda. Identify variables here. Lambda is given as x. If lambda is x, this is 1 over x as a variable. Whatever it is as a product with this is gradient. And this is my y variable. So the equation is y equals mx. Sorry, y equals m1 over x. Equation is y equals m1 over x. 1 over x means there is an inverse curve, right? Only inverse curve given here is 1. Right? There is an inverse curve. This is an inverse curve. There is an inverse curve. Only inverse curve given here is 1. Right? It's a simple graph. Right. Okay, then that particles and waves, X-rays and de Broglie, that part is over, and now we are moving to radioactivity. Right. Let's see. Radioactivity. First one. Which one of the following statements? Now, last week also, I think you have noticed that when it comes to questions of and radiation, you missed 6 questions. Did I? Ah, yes. Sorry. 6. I did the simplification of the previous question here, so I missed it. Right. Which of the following statements regarding the X-ray production in common application is incorrect? Okay. 2 circuits are used in X-ray production system. Yes. Right. There are 2 circuits. One is the main loop, and the second loop is the loop used to produce electrons. Right. There are 2 loops. Second loop is powered by the cell, and the main loop is powered by a high voltage difference. Right. So it is correct. Second one, anode could be damaged due to the bombardment of electrons. Yes, because electrons are hitting with the anode with a very high speed and it suddenly gets decelerated. So it is damaged. It's also correct. 3. Low voltage is sufficient to heat the cathode. Low voltage is sufficient to heat the cathode. Correct. Because to heat the cathode, we are using a small cell. Right? To heat the cathode, we are using a small cell. A small cell. Right? Correct. High voltage supply is to accelerate. Right? High voltage supply is there, that is to accelerate electrons. But to produce electrons, we need only a small cell. Then 4. Energy of X-rays emitted depends on the current through the filament. Energy depends on the current. No. Current depends on the number of electrons. Number of electrons. Current is about number of electrons. And energy is about acceleration. Energy is about acceleration. Right? Not the current. Energy depends on acceleration. Right? Energy depends on acceleration. Right? Acceleration changes when accelerating voltage. Accelerating voltage changes only. Right? Otherwise, current changes. Number of electrons emitted changes with the current. Right? Then current changes with the small cell. Cell current. Right? Energy is all about the acceleration. Simply kinetic energy. That is about acceleration. Right? Acceleration exchange accelerating potential, accelerating voltage, right? Provided between anode and cathode. So 4 is wrong. 4 is wrong. Let's check 5 as well. X-ray tube must be evacuated to avoid the energy loss of electrons. Yes. Always X-ray tube should be evacuated regularly. Usually it is done once in 2 minutes, right? Should be evacuated regularly to maintain the temperature inside the tube, inside the vacuum tube at a proper level. But otherwise, scattering of electrons increases. Scattering increases, then production decreases. Right? Okay. Now it's done. Right. Now we can move on to the next set, radioactivity. Right. Radioactivity. Right. Let's see. First one. Which one of the following statements made about X-rays and gamma rays are not true? X-rays and gamma rays. Okay. Right. First one. Gamma rays have shorter wavelengths than X-rays. Right. So we know in our electromagnetic spectrum, right, it goes as cosmic, gamma, X, ultraviolet, like this, no? Toward this side, lambda increases. Toward this side, frequency increases. Right? Now, it says gamma rays have a shorter wavelength. It's correct, no? Because towards the right side, lambda increases. Towards the right side, lambda increases. Then lambda of X is greater than lambda of gamma. Then lambda of gamma is shorter. Correct. Then gamma rays are shorter wavelengths. Yes, it is correct. Second one, gamma rays photons are charged, whereas X-ray photons are neutral. No, gamma rays are also neutral because gamma is 0, 0. Gamma rays are neutral. It has no neutrons, no protons. Right? Gamma is also neutral. So it is incorrect as a statement. Let's check the rest as well. It is incorrect as a statement. 3. Gamma ray, the more penetrating power than X-rays. Yes. Because gamma rays are very small rays, right? Since they are small, their penetration is very high. Right? 3 is correct. 4. Both gamma and X-rays travel with the speed of light in vacuum. Yes. Any ray or any particle in electromagnetic spectrum has velocity of light. Right? It is correct. Both are electromagnetic waves, no? Correct. Both X-rays and gamma rays can be diffracted. Yes. Any electromagnetic wave is a transverse wave. Any transverse wave can undergo all wave phenomena. So answer is 2. For first one, answer 2. Right? For first one, answer 2. Right. So when it comes to meta and addition questions, statement questions are also coming very regularly, very frequently. Right? I think last day also you have noticed it. Now today also we have, like, it's a mix of calculations and statements, but more frequently statements are also coming. So we have to be familiar, comfortable with the theory parts also, because they are basically on theory parts, no? Right? 2. In a radioactive sample, nuclei A decay to stable nuclei B. Right? A decay to B. A decay to B. The variation of number of atoms of form in B formed. Right? Formed means the production. Right? With the time. Right? We are drawing only two here, no? I mean, two variations here, no? One is about the decaying, decayed nucleus, decayed nuclei. Decayed nuclei is this one. This is the decayed one. This is the decayed one, and this is the formed one. Right? This is the formed one. So answer is 2. We have discussed them. We have only 2 graphs, decayed and formed. Right? එවනම් මතක තියෙන්න ඕනේ ඉතින්. 3. Which one of the following properties is not a common one of all 3 alpha, beta, gamma radiations? Okay. First one, carrying energy. Which one of the following properties is not a common one? Carrying energy. Yes, all of them carries energy. All of them carries energy. It is correct. Then second one, show particle as well as wave nature. Wave particle duality. Wave particle duality. Yes. Any particle, any matter shows both properties. No? Then it is valid for any matter. It is valid for any matter. This is called wave particle duality. This is called wave particle duality. Wave particle duality. Right? 3. Ability of ionizing air. Yes, all of them ionizes. All of them ionizes. When it travels through a gaseous medium, it is ionized. Being emitted by nucleus of an atom. Yes, inside the atom we have basically neutrons and protons. Right? Neutrons, protons means they can be alpha or gamma or any other type of a particle. And around the nucleus, outside the nucleus, if this is the nucleus, outside the nucleus, we have electrons. Then being emitted by the nucleus, yes. So they are with the nucleus. It's also correct. Having a charge, it's wrong. Having a charge is wrong because gamma is chargeless. Gamma is neutral. Gamma is neutral. Right? Gamma is a problem here. Gamma is neutral. Gamma is neutral. Other two has charges. Alpha is positive. Right? Alpha is positive. That is actually 2 plus. Alpha is a 2 plus. And beta is negative, -1. Gamma is neutral. Gamma is neutral. Right? Okay. 4. An isotope of uranium. An isotope of uranium, U-239 and 92, decays by the emission of alpha beta particle. Sorry, there's a small typo here. It should be a beta particle, not alpha beta particle. It should be a beta particle. Right? Correct it as a. Right? Correct it as a. An isotope of uranium decays by the emission of a beta particle. By the emission of a beta particle. Which of the following responses gives the correct mass number and atomic number for the new nucleus formed? Right. Now the isotope is uranium 239-92. Right. Now it is going to emit a beta particle. Right. Beta is 0 minus 1. Right. So we know when something leaves, when a particle leaves our radioactive sample, the respective numbers of protons and neutrons are taking along, right? Taking along with that leaving particle. Simple as that, right? Now, beta has no neutrons or protons, then this number remains same. This number remains same, right? And 92 minus -1 means it becomes 93. 92 minus -1, it becomes 93. So that's a new particle 6. Right? So here what happens is this is like 92 minus -1. 93. Right? Then mass number and atomic number is asked. Okay. Then atomic number is 93. Atomic number is 93. Mass number is 239. 239 and 93. Very simple. right? Very simple. Right? 5. A Geiger counter can be used to detect. Geiger counter. Right? Geiger counter. What Geiger counter does is it can deflect. It can deflect or deviate alpha and beta because they have a charge, right? Because they have a charge. Gamma or neutrons cannot be deviated because it doesn't have a charge, right? Then Geiger counter can be used to detect alpha particles, yes, because they have a charge. Beta rays, yes, because they have a charge. But neutrons we can't because they don't have a charge, right? Then only alpha and beta, only A and B, right? Now, if all three are deflected at once, through the Geiger counter, then neutrons can also be detected, because if other two are detected, the remaining one should be the neutron, no? Otherwise, now if we enter like neutrons with something else other than alpha or beta, then we can't say anything, right? Now, in this particular year, both 4 and 5 were considered as answers, I mean correct answers, because if all three are inserted to the Geiger counter, if all three are given to the Geiger counter, when alpha and beta identified, neutrons are automatically isolated, no? Then for that reason, both 4 and 5 were given the marks, right? But the best answer here is 4. Best answer here is 4. Right? Best answer is 4. 6. 6. A radioactive element XA86 decays to a stable Y8226 after several alpha emissions. It should be several alpha emissions, not A emissions, several alpha emissions. After several alpha emissions, the value of A is okay, right? See, then this Xc is decayed now. Xc is AN86 no. Now it is decayed to Y82 206, right? I'm going to balance the equation. I'm going to balance this nuclear equation. Now after alpha emissions, no, alpha is 42. Right? Now if you check atomic numbers here 86, but this side that is only 82 plus 2 84. There's a short of another 2, no, which means if 2 alpha particles are used, it is going to balance, no. Now it's correct. 86, 82, 2 times 2, 4, 86. It is balanced. 2 alpha particles. Right. Now balance the mass number. This is 206 here, and 4 times 2, 8 here. This is 8 here. 206 plus 8 means 214. Right? 206 plus 8 means 214. Then this must be 214 to balance the equation. So that is 214. See how easy these questions are if you know these theories properly. Right? See how easy the questions are. You have to know the theories. That's it. Right? Know these theory parts properly, then easily you can get this mark. Right? When it comes to matter and radiation, these MCQs are very easy. So easily you can score. That's the advantage. So that's why I finished these lessons in December and January, right? In the reverse class, right? Lessons like properties of matter and radiation. Easy lessons. Okay, 7. Radioactive. This is a small mistake. This should be switched. 234 here and 90 here should be switched, right? So it should be 234 and 90 like this. It's a typing error. 234 and 90 like this, right? Radioactive. The nucleus emits 2 beta particles, beta emissions, followed by an alpha emission. The resulting nucleus will have. Okay. Now first it is going to emit 2 beta. Right here it is going to emit 2 beta. Right. So we know beta is 0 minus 1. 0 minus 1. So it is not going to change the atomic number, sorry, mass number, but atomic number will be changed by minus 2. Minus 2 means it is going to minus 2 plus 2, then 92, right? A different particles, A, X, right? And then followed by alpha. Alpha is 42. Alpha is 42, right? Alpha is 42. When 4 is removed from here, this becomes 230. When 2 is removed, this becomes 90, right? So again, this is an isotope of this TH, 90 and 230. Question is about number of protons and neutrons. So we know at the atomic number we have number of protons. At the mass number we have the addition of protons and neutrons. Then protons is 90 protons and 140 neutrons, right? 3. Right. So again, an easy question, right? Give me 1 second. Take down if anything. Okay. Right. Next. Ask if there's anything. Right. Next, 8. A fossil is found to be 72,000 years old by carbon-14 dating. If the half-life of carbon-14 is 6,000 years, the ratio amount of carbon-14% in fossil over amount of carbon-14% in living tissue is, right? Then 6,000 years, no? So first we can check how many half-lives are passed. One half-life is 6,000 years. Then number of half-lives passed is 72,000 over 6,000. These three cancels. 6 times 12, right? 6 times 12, yes, 12. So we know for a radioactive sample, N is NO over 2 to the power N, right? Where N is the present number of nuclei, right? This is the present number of nuclei. This is present, right? This is original. NO means original, present and original. Now, what's the ratio we need? Amount of carbon-14 present and amount of present in carbon-14 present in the living tissue. Living means original. Then I need NO. Then NO is 1 over 2 to the power N. N is number of half-lives. Then 1 over 2 to the power number of half-lives is 12. 1 over 2 to the power 12. Very simple. 1 over 2 to the power 12. Right? 1 over 2 to the power 12. Simple. Next, 9. A radioactive nucleus X is a day decays by emission of an alpha particle followed by a gamma ray. The daughter nucleus thus formed has a mass number and atomic number. Right. Radioactive nucleus is X, A, Z. First, it is going to emit an alpha. Alpha is 42. When alpha is emitted, this becomes A minus 4. This becomes Z minus 2. Right? Say the new one is Y, something like this. And followed by gamma rays. Doesn't matter because gamma is 0, 0. Nothing is going to be different when gamma leaves. Only the energy of the system decreases. Then here also the same Y remains, A minus 4, Z minus 2. Then A minus 4 and Z minus 2. A minus 4 and Z minus 2. Simple. 9, it's 2. right? See how easy scoring these questions are. That's the benefit. That's the advantage. That's the benefit you have, right? When it comes to these lessons, right? So still you got 12 weeks. If you haven't practiced these questions yet, practice them. Now in the paper class also, I was discussing these questions in all the papers now after finishing the lesson, right? So you also have an idea about how easy the questions are compared to the other questions we have, right? So if you know the theories properly, if you are comfortable with the question, easily you can score like 27, 28 marks out of 30 without any hassle if your knowledge is good enough. That's the thing. So easily you can score in less time. Right. Next 10. If the mass of a radioactive sample is doubled, which of the following is correct regarding its activity and half-life? Right. Activity depends on number of nucleus, no? Right. Activity depends because we know equation of activity is R equals minus lambda n. Right. So higher the number of nuclei, higher the number of nuclei, higher the activity. Higher the number of nuclei, higher the activity. So activity increases. Activity increases. And about half-life, we know, right? We know lambda is given by 0.693 over T half, no? Right? Then T half is 0.693 over lambda. Lambda is a constant. Lambda is decay constant. 0.693 is a constant. Right? This is a constant. This is a constant. So T half is a constant. T half is a constant. Then activity increases, but half-life remains constant. 3, right? Yeah. Activity increases, half-life remains constant. Right? Simple things. Simple theories. Next. 11. The variation of rate of decay A of a radioactive sample with time t is given by the relationship A equals A O e to the power minus lambda t. The dimensions of A is right. So we know A is activity, right? Rate of decay is also called activity. A is activity, right? So rate of decay is written as N over T. N is number of nuclei. It's a number, dimensionless, right? Dimensionless. It's dimensionless. But this is time. Time has a dimension. Then dimensions of A is T minus 1. Simple. Dimensions of A is T minus 1. Right? Because this is the exponential function. This part doesn't have any dimensions. Exponential function is again constant, no? 12. Consider the following statements regarding alpha and beta particles. Okay. A. Both alpha and beta particles travel with the speed of light. Correct, no? Both alpha and beta particles travel with the speed of light. Correct. Oh, wait. Consider the following statements regarding alpha and beta. Both alpha and beta particles travel with the speed of light. No. What's the reason? When it comes to alpha and beta, right, they are not electromagnetic waves, right? If they are not electromagnetic waves, they don't travel with velocity of light. If they are not electromagnetic waves, they don't travel with velocity of light, right? If they are electromagnetic waves, they travel with velocity of light. Then this is less than speed of light. B. Generally, alpha particles penetrate deeper into materials than beta particles. No, because alpha is a larger particle. Alpha has 4 and 2, right? Then 4 nucleons. Alpha is a larger particle. Alpha is larger, right? Right? More larger means lower penetration, lesser penetration. That is also wrong. Right? C. Both alpha and beta particles can ionize atoms when they travel through materials. Ionization is done. Ionization is done. They ionize metals and gases. Right? They ionize metals and gases. Then C is correct. It's only C. Right? It's only C. Or simply alpha means helium particles. Huh? Alpha means helium. Helium nuclei. Helium nucleus. Helium nucleus. Right? Helium nucleus. 13. The radioactive nucleus XAZ decay to A minus 4 Z minus 1 in two stages. The radiation counted these two stages would most likely to be right. So initially it has been A and 0. Then finally it is A minus 4. Right? Z minus 1. It's a different one y. Right? So when I see this minus 4, right? So at once what is coming to my mind is alpha. Because alpha is 4 2. Alpha is 4 2. Right? Then if one alpha is removed, alpha is 4 2, no? If one alpha is removed, alpha is 4 2. Alpha is 4 2. Right? Now try to balance this. Try to balance the equation. Now this side is Z. This is Z minus 1 plus 2 means C plus 1. C plus 1. Again, it should be balanced. To balance it, now if we use a beta, beta is 0 minus 1, no? Check now. C minus 1 is minus 2 plus 2, C. Then A minus 4 plus 4, it's A. So this is a balanced equation now. This is balanced. Right? Since that is balanced, it should be an alpha and beta. Alpha and beta. First one. Alpha and beta. Right? Alpha and beta. Right? So without writing the balance equation, if you can just argue, because when one alpha particle leaves, it becomes A minus 4 and Z minus 1. Right? Then again, Z minus 1 should be increased to, sorry, Z minus 2. And Z minus 2 should be increased to Z minus 1. No? Then another beta should be left. Beta should be left. Beta should be left. So likewise, arguing is also fine. Arguing is also fine. I wrote the equation to all of you to understand. Otherwise, arguing is also fine. Totally fine. 14. An archaeological extracted 100 milligrams of carbon from an ancient wooden tool and found it 1/4 as radioactive as 100 milligrams of carbon extracted from a live tree. Half-life of carbon-14 is 5,730 years. How old the wooden tool? Right. Okay, 1/4 is radioactive. Right. Using radioactivity, we can apply this equation. No? Activity can be written as R equals R rho over 2 to the power n using activity. Right. Then the present one is 1/4 times radioactive. Then if the original radioactivity is 1, the present radioactivity is 1 over 4. If originally is 1, then 1 over 2 to the power n. Cross multiply. Then 2 to the power n equals 4. 2 to the power n equals 2 to the power 2. N equals 2. What's the meaning? 2 half-lives are passed. 2 half-lives are gone. That's the meaning. 2 half-lives are gone. 2 half-lives are gone. And if 2 half-lives are gone, then age is how old? Then the age is 2 half-lives are gone. 2 times half-life is this much. So that is 11,460. 11,460. Right? 11,460. So if you know correct theories, easily you can tackle the questions. Right? Easily you can tackle the questions. This is all about knowing theories. Right? Solid knowledge on theories. Right. 15. Right. 15. A radioactive source is placed at the bottom of a hole in a lead block. The beam of radiation through the hole is allowed to pass through a magnetic field as shown in the figure. Right now, this has a small connection with magnetic fields now. Right? Forces acting on charges in magnetic fields. Right? as shown in the figure. Three separated beams A, B, and C could be. Three separated beams A, B, and C could be. Okay. So B is not deflected. Since B is not deflected, B is obviously gamma because it is chargeless. It is neutral. That is why it is not deflected. Right. So this side of the magnet is given as N. This side of the magnet is given as S. So we know magnetic field is always from N to S. Magnetic field is always from N to S. Right. And force on a charge is given by Fleming's left hand rule. Apply Fleming's left hand rule, right? And apply Fleming's left hand rule and find the respective direction of force. Right? Now, if I apply left hand rule for this one, if I apply left hand rule for this one, right? Then direction of magnetic field is N to S, right? Like this, direction of magnetic field is N to S, right? Then direction of force has been the same direction, and it says current is same. If the current is to the same direction of motion, there is a positive particle. If the current is to the same direction of motion, there is a positive particle, which means this has to be alpha. This has to be alpha. If there is alpha, this is beta. Then it should be alpha, gamma, and beta. That is 4. Right? Fleming's law part is coming from magnetic fields. Fleming's law part is coming from magnetic fields. Right? 16. When an atom of radioactive element emits a beta particle, it is transformed into an atom of a different element. A different element is formed in this manner because, right, emits a beta particle. So what happens is this, no? Say X emits a beta particle. It had A and B, mass number and atomic number. So when it emits a beta particle and forms Y, let's say, when it emits a beta particle, what happens is 0 minus 1. So what happens is this becomes B plus 1. This becomes B plus 1. And this becomes A. Right? A remains constant. No? A remains constant. What is the idea? Number of protons and neutrons, addition of protons and neutrons remains unchanged. Right? But we know atomic number is number of protons. That is increased by 1. Right? Without changing the addition of protons and neutrons, only a proton is increased, which means 1 neutron here. Right? Get this idea properly. 1 neutron here should be converted into a proton. 1 neutron here should be converted into a proton. Then the addition of neutrons and protons remains unchanged, N plus P, but the proton number increases. Right? Number of protons increases. Then a neutron is converted to a proton. Then it should be a neutron in the nucleus in the radioactive element changes to a proton. Yes, it's 4. For 16, it's 4. Right? Right. Give me 1 second. Take down if anything and ask if there's anything to know. Okay. 17. Right. 17. It's a unit of activity of a radioactive element is. Activity is becquerels. Right? What is Curie? Curie is the SI unit of radiation. Becquerels is activity. Activity means radioactivity. Right? Geiger is also a unit of radiation, not the SI. not the SI, but it's a unit of radiation. Sieverts is the SI unit of absorption dose. Absorption dose. Radiance is angles, no? Right? So that is becquerels. 18. Radioactive element 230-90 transforms to stable 208-82 after several radioactive decays. The number of particles and the number of, it should be number of alpha particles and the number of beta particles emitted. Number of alpha, number of alpha particles. Correct it. Number of alpha particles and number of beta particles emitted in the decay, respectively. Right. So here we have 232-90, right? And it has transformed to 208-82. So we know, right? Listen, we know alpha is 42 and beta is 0 minus 1. Beta is 0 minus 1. So beta is not going to change the beta is not going to change the mass number. Beta is not going to change the mass number, right? Then mass number change is totally due to, it should be totally due to alpha emissions, no? Change in the mass number should be due to alpha emissions. Change in the mass number should be due to alpha emissions. That's the point. Then 232 is deducted to 208. What's the difference? 232 to 208. So the difference is 24, right? Yeah, 24, no? 24, no? Then difference is 24. One alpha particle is, right? One alpha particle has 4 nucleons. Then to emit 24 nucleons, there should be 6 alpha particles, right? So that's the first point I got into the question, right? 6 alpha particles. It should be 6 alpha, right? Which means now I can write the reaction here to some extent 6 alpha. Then 4 and 2, 6 alpha, right? 6 alpha. Now, if you check the mass numbers, it should be balanced. 232, and this is 6 times 2, 24. 24 and 208, 32, it's balanced, right? And check the atomic numbers. 90 here. This is 84 here. 90 and 84, right? Yeah. 90 and, 84, 6 into 2 and 12. Then 82 plus 12 is 94. Then 94. Then this is 94. Let me minimize this a bit. Okay. See? Now, this is balanced already. And here in this side, we have 82 and 6 times 2 is 12. Then 82 and 12 means 94. 96 and 92, 94, 94. So here we have 94. It should be 90. Then this side is having additional 4 compared to left hand side. To remove that additional 4, if we have 4 beta particles, 4 beta, it is going to create this minus 4. See, it is going to create this minus 4 here. Now check the equation. 90, 82 plus 12 is 94. 94 minus 4 is 90. It's balanced. So which means 6 alpha and 4 beta. 6 alpha and 4 beta. Right? So this is the first point I got in the question. It was 6 alpha particles. Then if I know it has 6 alpha, then to balance the atomic number, you can check the number of beta particles to balance the atomic number. Simple as that, right? Next, 9-18. In the nuclear reaction, particle denoted by A is this should be A, not alpha. This should be A, right? There are small typos here. I don't mind. Make these changes. Right. Now, balance this. Left hand side we have A plus 7. Let me write the equation again. 7, 3 plus X, A, Z, and X, A plus 6, right? Z plus 2 plus A. Balance these numbers. Here we have 3 plus 2. Sorry, 3 plus Z, 3 plus C. This is Z plus 2, then it should be 1 here to make it Z plus 3, Z plus 3, right? Then here we have 7 plus A, 7 plus A. This is A plus 6, then this should be 1 again. Now it is balanced. Left hand side also we have A plus 7. Right hand side also, that is A plus 6 plus 1, A plus 7. Atomic numbers 3 plus C, this is Z plus 2, Z plus 2 plus 1, Z plus 3, right? Then 1 1. 1 1 means what? 1 1 means this is a proton, because there is 1 1, no? So likewise you can identify the particle. Proton 1 1. 1 1 means it's a proton. 1 1 means it's a proton, right? 1 1 is a proton. 20. The radioactive isotope of iodine decays to, right? What type of particle is emitted in the decay? Right. Iodine 131, 53, right? And it has become xenon 54, 131. Very straightforward. No change in the mass number, but atomic number is increased by 1, right? So easily you can guess even without writing. That's a beta particle. That's a beta particle, no? Right? You can check even without writing. That's a beta particle, right? Then 0 minus 1, right? That's a beta particle, right? If the atomic number is increased, right? Increasing is always due to beta. Increasing is always due to beta, because that's the only particle we have a negative charge there, right? 21. A slow neutron is absorbed by a uranium nucleus and results in a fission process as follows. Right. The value of X number of neutrons produced in the fission process is, okay, balance this equation. Now this side, if I check the atomic numbers, see, if I check the atomic numbers, 0 here, 92 here, then there is 92. Here 56 and 36. 56 and 36 means 92 is balanced. Yeah, it says it's neutrons, no? So 92 is balanced. Then check the mass numbers. 1 and 235 means 236 here in this side. And here 139 plus 94. 139 plus 94 means 239, 233, right? Yeah, it is 233 on the other side. Then the balance is 3, no? Balance is 3. To balance that 3, if there are 3 neutrons, it is going to balance, no? To balance that 3, if there are 3 neutrons, it is going to balance. Now check it again. 236, 139 plus 94 is 233 plus 3, 236. It's balanced. Then it is 3. Right? See how easy the questions are. Right? That's how it is. Right? Next. 22. A radioactive material has a half-life of 60 minutes. The percentage of fraction of material that has decayed during a period of 3 hours is, right? 3 hours means 3 half-lives are gone, no? 3 hours means 3 half-lives are gone, right? Which means 3 hours sorry, 3 hours. 3 hours means 180 minutes, right? Then one half life is 60 minutes, which means 3 half lives are gone, right? 3 half lives are gone. 3 half lives are gone. So we know n equals no over 2 to the power n. N equals no to the power n. Decayed fraction is asked, the percentage of the fraction of material that has decayed, right? So here we have the present part. This is the present and this is the original, right? Now see what has happened. Now n over no is 1 over 2 to the power n is 3, right? Which means n over no is 1 over 8. N over no is 1 over 8. What's the meaning? What's the meaning? Present number of nuclei in the sample is 1 over 8. Present number. If present number is 1 over 8, decayed number should be 1 minus 1 over 8, no? Right? Because now the remaining part is only 1 over 8. Remaining part is only 1 over 8. If the remaining part is 1 over 8, right? 7 over 8 is already decayed. So therefore, right? Therefore, decayed fraction is 1 minus 1 over 8 decayed fraction. That is 7 over 8. Then get the percentage into 100%, 87.5. 87.5. Right? Again, a simple question. Again, you should know the proper theories. That's it. Theories done at you should know the proper theories. This is the advantage of doing these type of questions. Now, compared to other questions like mechanics, waves, optics, thermal, right, electricity. See how easy these questions are. They are MCQs, right? Each question carries 1 mark, right? Each question carries 1 mark, right? So don't lose these marks because they are easily gettable, easily doable, easily gettable. That's the benefit. That's the advantage, right? Let's move on. 22. The following table shows the binding energies of some nucleus binding energy. Which of the above nuclei is most stable? Right? If you need to check the stability, right? Check binding energy per nucleon. Right? Higher stability means, right? Stability is proportional to binding energy per nucleon. Right? Now, first you have to find the binding energies per nucleons. Number of nucleons are here: 4, 20, 40, 60, 238. Right? Then I need per nucleon values. Right? So let's find the nucleon per nucleon values. Then for the first one, it should be 28.3 over 4. Right? Next one, it is 160.6 over 20. Next one, that is 342.1 over 40. Right? This is 526.8 over 60. Last one, 1802 over 238. Right? Check these numbers. 28.3 over 4. 7.075. 7.075. These are some close numbers given, right? Doesn't mean you need to check all of them, right? But some close numbers are given, right? This is 160 something 8.03. Then 342 over 40. 342.1 over 40. 8.55. That's why I told you close numbers are given 8.55. Then 526. 526.8 over 60. 8.78. Close numbers 8.78. Right, last one 1802 over 238, 7.57, right? So it's very clear that highest number out of all is, right, this one, no? So it is going to be nickel. It is going to be nickel, right? Nickel. It is nickel. Right. So likewise, you should know proper theories. Right. That's playing the role here. Questions are easy. That's playing the role here. Next, 24. The SI unit used to measure the activity of radioactive sources. Kalanut tibba. We met the same question before. Right. Kalanut kalla activity. Activity means radioactivity. Radioactivity is measured in becquerels. Right. Geiger is radiation, not a SI unit, but a unit of radiation. Right. This is a different unit. I mean, meaningless, right? Sieverts, uh, absorption, right? Sieverts means, right? Before also I mentioned you, this is the absorption dose, right? That is becquerels, very straightforward, becquerels. 25, radioactive element X ZA transforms to stable 82 to 106 after emitting 8 alpha particles and 6 beta particles in successive decays. The number of protons and neutrons in the element X respectively are. Okay. Okay. Now the reaction has been XAZ and it has been transformed to 206 and 82. It clearly says it's emitting 8 alpha and 6 beta. Right? I'm going to balance this equation. See, going to balance this equation. Alpha is 42, beta is 0 minus 1. Right? Balance the equation. Balance the equation. That's it. Balance the equation. Check atomic numbers 82. 82. This is 8 times 2, 16. 82 plus 16 is 98. 98. This is minus 6. Minus 6 means 98 minus 6, 92. Then this should be 92. This should be 92. Then check the mass number. Right? Simple. 206 here. 206 here. Here 8 times 4, 32. Right? Then that is 206 plus 32. And here 0. Then this is 8, 238, right? Then this is 238. So it is 238 and 92. What is asked? Number of protons and neutrons. Right. Now the addition is 238. Final answer. This is not the final answer yet. Right? So number of protons are 92. This is number of protons, 92. This is the addition, no? This is the addition. This is the addition of protons and neutrons. Then 238 minus 92 means 146, right? 238 minus 92, 146. Then number of neutrons should be 146. Then 92 and 146 answer 2. 92 and 146 answer 2. Right? So same questions are coming in different ways. Right? So they are easily manageable as long as you know proper theories. Right? Easily manageable as long as you know the theories properly. Right? Right. 1 second. Take down if anything and ask if any questions. Right. One second. Okay. Then 26. 26. 26. Consider the following statements about the half-life of radioactive atoms in a sample. Right. Half-life. Right. We got a question before also from the half-life, right? Yeah. T half changes with the number of radioactive atoms present in the sample. No. Because T half is 0.693 over lambda. T half is 0.693 over lambda. T half changes with the number of radioactive atoms present in the sample. Wrong. Right? T half changes with the date and time of the prepared sample. No. Date and time of the prepared sample. No. Right? T half depends only on lambda. T half does not change even if the radioactive atoms are ionized. Yes. Right? No problem because T half depends only on lambda. Only on lambda. C is correct. So that is only C. Only C. Right? C is correct. Only C. Only C. Right? 27. 27. Then uranium 92 to 135 nucleus is bombarded with a slow neutron. The following nuclear reaction may take place. The values of A and B. Values of A and B. Okay. To find A, right? So before finding A, are neutrons. So we can find A first. Neutrons means 1 and 0. No? Right? Let's find A first. Let's find A first. Check the atomic number. Check the atomic number. This is 1, 1. Oh, sorry. One second. One second. Okay. Let me share this again. Right. Okay. Now again visible, right? See? So we were in question 27. We were in question 27. When uranium nucleus is bombarded, okay. Now first I'm trying to find A. First I'm trying to find A. First I'm trying to find A. Right? To find A, check atomic numbers. Check atomic numbers. Neutron is 1, 1, no. Then this side we have left hand side. Let me write the equation here again. That is much easier to be 92, 235 plus neutron 1, 1. It gives X 44, 102 plus Y A N 131 and B neutrons. Neutron is 1, 0. Right. Neutron is 1, 0. Then this side is 93, no? 93. Here we have 44. We have 44. Right? If there is 44, the remainder should be balanced by this A. Then 93 in 44 plus it should be 44 49. 49. Because 44 and 49 is 93, no? 44 and 49 is 93, right? 44 and 49, yes. Then, listen, this should be 49. It is 93 now. That part is balanced. That part is balanced. Then, check the mass numbers. Here we have 236. 236. And here 102 and 131. 131 and 102 means 133, no? Sorry, 233, no? 233, right? Then this side is 233, 36, which means the difference is 3. Then to fill that difference, we need 3 neutrons. We need 3 neutrons. Then 49 and 3, it's 5. 49 and 3. 5, not a big deal again, not a big deal. 49 and 3. Right? Just balance the protons, number of protons and number of neutrons at the other sides of the equation. Balancing nuclear reactions is very easy. Balancing nuclear reactions is very easy compared to chemical reactions. Right? Okay. Moving on. This is not partial. This should be particle. Particle physics. Particle physics. Right? Particle physics. Let's move on. Right. Particle physics means that's a new part put in 2019 about quarks, leptons, antiquarks, electron, muon, tau, up quarks, down quarks, charms, strains, top, bottom, right? Those are the things, particle parts, right? First one, according to the evidences found in particle physics, matter composed of 12 fundamental particles, right? It composed of 12 fundamental particles, right? 6 quarks and 6 leptons. Then 6 quarks and 6 quarks and 6 leptons. It should be 6 quarks and 6 leptons, right? Straightforward theories. 6 quarks, 6 leptons. Second one, the quark content of a proton P and a neutron N are respectively given by quark content of proton and neutron. Again, very straightforward. Quark content of a proton is UUD. Proton is UUD, right? Neutron is UDD, right? So it is 4. Right? So we'll discuss these things in the class. Very straightforward and simple. 3. What is the charge of a down quark in the elementary charges? One answer is not properly printed here. Correct one answer as, it should be this one. Correct the third answer as -1/3. Right? That is the correct answer. What is the charge of a down quark? So we know about charges, right? Charge of an up quark is, charge of an up quark is +2/3 of an electron. Charge of a down quark is -1/3 of an electron. Right? So these are the charges we have. These are charges. Right? 4. What is the charge of this is not U. Mistake. This should be U bar. This should be U bar. What is U bar? That's a small typo. Correct it. That is U bar. What is U bar? Right? U is up quark. U means up. U is up quark. Right? U bar is anti-up quark. Right? U bar is anti-up quark. Anti-up quark. Anti-particle. Anti-up quark. Anti-particle means, what is the anti-particle? In positron I discussed. Anti-particle means the particle has same mass, same charge, everything. Only the polarity is different. Anti-quark means, right? Only the polarity is different. So with different polarity. Different polarity. So we know up quark is plus 2 over 3, no? Then anti-up quark is minus 2 over 3. Up quark is plus 2 over 3. Anti-up quark is minus 2 over 3. Right? Right. So we have come to the end. Any questions? So in the 27th question, is in the answer 327. 27. 92 plus 1 is 93, right? 92 plus 1 is 93. Then this side, it was 44 and it was 44. Sorry. Neutron sorry. Thanks for saying it. 1 Newton, 1, it is not 1, it is 0. Right? This should be 0, sorry. Thanks. So mistakenly, I have put 1 here for the Newton. This is 0. Right? Then it is 92 this side. Let me do the corrections here itself. It should be 92 this side. 92 again. This is 48. Ne? Yeah, 48. Then 48 and 3. Yeah, 48 and 3 again, it's 3. Yes, it's correct. Right? Yeah, so likewise, if you notice something, quickly tell me. Right? The mistake was here. Newton is 1, 0. Right? I have put 1, 1 mistakenly. Right? 1, 1 can proton. Proton is 1, 1. Now it's fine, right? Aisha, now it's fine, right? Aisha, right? Yeah. 92, now it becomes 48. 48 and 3. 48 and 3. Right. Anything else? Anything else? So have a note on this. I mean, keep a track, have a note on this antiquarks. Right? For any particle, we have antiparticles. For any particle, we have antiparticles. Antiparticle is the particle with same features but with different polarity. Right? Same features with different polarity. That is what we call the antiparticle. Right? A popular antiparticle we had is beta and beta plus, beta and beta and beta plus, electron and positron. Popular antiparticles. So likewise, for any particle exists in the world, we have an antiparticle. For any particle. Right? Only difference between that original particle and the antiparticle is only the polarity. Only the polarity. Right? Only difference is only the polarity. Right. Right. So here also, I think we have discussed like 38 MCQs today. And with this, right, with this, we have discussed all around 70 questions over there from meta and radiation, 70 MCQs, all are discussed. Right, we have come to the end of all meta and radiation questions. Next week, we'll be taking something from thermal or let's see, from thermal, low current electricity or something else. Right? You can get all the updates through my channels. Right? So we'll be taking it to the discussion accordingly. Right? So probably I'll be taking something from thermal, low electricity. Right? Since electricity is also now done, I have an idea to start electricity questions here also. Right? Let's see how it goes. Right? I feel starting electricity is better. Let's see. You can get all updates through the channels. Any other questions? Anything else? Right? So we have come to the end of all 35. Will you discuss only the MCQs in the session? No. After discussion of MCQs, I'll start structured essays and essays. Right? So after MCQs, we'll start structured essays and essays also. Right? So first, to expand knowledge, discussing MCQs is better, because when we discuss MCQs, always you have to think of different things, different areas, different parts, different things you have in your head when we are switching between MCQs, right? When we are switching between MCQs. Otherwise, when we do an essay, right? Say the essay is from a particular part, say from black body radiation, then always you are thinking only about black body radiation, no? But when it comes to MCQs, always it switches, right? Right. Okay. Starting electricity, yeah. So I thought of starting electricity or thermal. Probably we'll go with electricity. Let's see, right? Okay, then. If no any questions, we can wind up, right? If no any questions, we can wind up, right? If you have anything to know, you can ask. If you have anything to know from my side, you can ask. Anything else? Anything else regarding S2As or something else? Any other subject matters or classes? Right? Let's see. Sometimes I might take some structured essay questions next week also. Let's see. Right? I haven't decided yet. Right? I haven't decided yet. But I have different things in mind. So we'll do something accordingly. Right? Because now this is day 13 of S2A, and in all 13 days I have discussed MCQs, no? Right? So sometimes I might be taking structured essays next week. Api balamu, mark kara ekak balamu. I will update you through the channels. Right? Okay then. Then if no questions, we'll wind up. Right? Okay, then again, reminding again, we are just 12 weeks from the exam. The most critical 12 weeks is going on. We are from 12 weeks from the exam. Right? So study hard, work hard without wasting your time. Right? That is exactly 12 weeks and 3 days now. 12 weeks and 3 days now. Right? So work hard, work hard. Right? This story is going to be over in another 14 weeks after the exam. Right? To start the exam, you have 12 weeks. To finish the exam, you have only 14 weeks. Right? Time flies these days. So you are going to decide your life story during these 12 weeks. Right? Okay then. Right? Okay, then I'm going to wind up. Spend this time wisely, right? Without wasting. Spend it wisely, right? Be clever, be smart, and put your maximum effort, right? Do everything in an organized manner, right? Do everything in an organized manner, right? Have a plan. Have a plan. I have discussed in the schedules and plans in the classes, right? And I put some past paper plan on. I share it on my YouTube also, right? About the past papers, especially, and other working plans I have discussed in the class, right? So somehow have a plan to yourself and uh, work accordingly, right? Then if no questions, will wind up. Then stay safe and work hard. Good night and goodbye. See you next class, right? Goodbye.